All right, good morning. We're going to get started with, I'm going to bring up one of the sheets that we worked on together last class. I want to clarify some of the points that we finished with, and then I'll take questions on the homework. So grab your homework out. Let's take a look at something from last class, and then we'll get into new material for today. And it's not terribly intense compared to last class. I sort of promised. Okay. You should recognize this page. It's from last class. It's the one I wrote out in fourth period, but it should look pretty similar to the one we did in our class. There's a couple things I want to highlight here. I'm going to just bring up my drawing tool. And there we go. All right, over here on the right, this is, I'm sorry, the left. I don't know my left from my right. When we were doing this work, in this case, we changed the acceleration, or alpha went to acceleration, or A over R, the radius. Then we changed that acceleration to gravity. That happened up here at the top. I can circle those two, and the gravities cancel out. I want to make sure no one believes that that acceleration alpha going to A over R, that acceleration is not gravity for each and every single problem. It was a special case for this problem, so that's why I wanted to highlight it. I'm going to scroll the page down a little bit and see if we can get to the image. The image was talking about the acceleration from these two blocks. Those blocks are in equilibrium and they're hanging objects. Since they're in equilibrium and they're hanging objects, the source of the acceleration is gravity. So that A is not going to be G every single time. And it's a special case here because they're hanging objects. So we have mg down and tension up, and they're in equilibrium. And so the only acceleration is going to be from, the only source of acceleration on these objects is coming from gravity. And that's why we were able to make it G for that case. I also want to point out that for torque, when we changed I alpha into M1 R1 square, I didn't put any fractions there. And the reason I didn't have to, no matter what the fraction would have been, is the torques are balanced. So if it was 1/2 mr square, if it was 2/5 mr square, if it was 1/12 mr square, whatever the fraction on the left would have equaled a fraction on the right for what the rotational inertia would have been. Since it's the same, it didn't have to be included. So it's not something that you have to consider. When you put the two torques equal to each other and they're from the same system, or for the same object that would be rotating, or the same type of object that would be rotating, there you don't have to include the fractions because they would just cancel out. Now, the reason that on the right side, now I really do mean the right side, when we come over to the right side, and in red, I'll put a big arrow right there, there, I also turn torque into I alpha, and I is just simply mr square. And I think this came up later in the day, and it came up in questions through email and through tutorials, is why was I just mr square? Is torque just always mr square? Torque isn't always just mr square, but for this particular problem, we were looking at point masses. The rod itself had a negligible mass. It's like the rod doesn't exist. They're connected by a rod that has no mass, is what the problem is saying. So we didn't consider this a rod that's pivoting in the middle when we look at rotational inertia. What we're looking at is okay, well, we've got point masses. In point masses, use your raw formula, I equals mr square. It is a bit confusing, especially on the first day going through it. So I wanted to highlight some of these details because it makes a difference as we go into the homework. All right, all that to say is now let's go into the homework. What we assigned is I think we assigned the whole page. I don't think we had any time really to spend in class to do this together. I believe this is the page. Yeah, that looks about right. Go ahead and open this up. I'm happy to take questions on this page for a couple of minutes before we go into today's work. So if there's any specific ones that we need to look at, let's do that now. So either audible or text. I'll give you a second to find the page and let me know if there's anything that you just struggled on that we need to look at together. Can I review question 9? Absolutely. So the question to me was to review question 9. So let's take a look at question 9. Well, tell it that I have a tool. Okay, so question 9, we're going all the way to the bottom, which is good because it looks like, you have to work through the thing to get to the last question. Let's take a look at it. A ring and a disc of equal mass. Okay, so I'm kind of a margin guy. I like to put notes in the margins. I like to list things out and draw pictures from time to time. So if I've got a ring and I've got a disc, do a little bit better G. Okay, and then my picture of a ring would look something like this. So there's my mass all to the outside edge. And then I've got a disc, and this guy's going to be filled in because the mass fills in across the disc. We kind of know that. They have the same mass and the same radius. Okay, so mass is M, mass is M. Let's make radius R, radius R. So they have the same mass, same radius. What else do we know about a ring and a disc? We know that for a ring, just kind of making notes here. So we've got some things to use when we get to the questions. I equals, should be MR squared. And then with a disc, here the mass is brought in closer to the axis of rotation or the pivot point. And so we know that I is going to be smaller because the distribution of the mass is closer to the point of rotation. So we know we're going to have a fraction here. So for the disc, wasn't it a half? Yeah, that's what I have in my notes, 1/2 MR squared. All right, so we've got the information that we know so far. If both race down to the bottom, which will finish first? All right, use any equations that you need and explain how the equations support your conclusion. I'm sorry, let me add somebody to the party. Hey, good morning. We're on number 9 from the homework. This is the one that we're going to review before we go into new material. At least it's the one that was requested, so it's the one we're going to do. Okay. Now, from what we've written, we know that they have the same R's, the same M's, the same masses, the same radiuses. Those radiuses are going to be squared. But with a disc, we have that 1/2. Okay, so we know that overall, their rotational inertia is smaller just by the formula. Okay, if the M's are equivalent, the R's are equivalent, but the disc has that pesky little 1/2. So that means it's going to be half the size for rotational inertia than the ring. And let's just define what I means. It's the moment of inertia or rotational inertia. So I is the rotational inertia. Okay. That is the object's tendency to resist rotation. Okay. I is the rotational inertia, and that is the object's tendency to resist angular rotation. And it's angular rotation that's going to get the disc to the bottom, right? Or the ring to the bottom. They're going to rotate and they're going to rotate to the bottom. Let me let somebody else in. The party gets bigger. All right, welcome to the party. We are on number 9 from the homework. Now we've identified the ring as having a larger rotational inertia or a moment of inertia, and the disc is smaller because they have the same mass, they have the same radius. So all that kind of cancels out, but the disc has that 1/2, making it smaller. So it has less of a resistance to rotate. So it's more free to rotate, it's more willing to rotate. Since the disc has that lower moment of inertia or rotational inertia, it will accelerate faster. And if it accelerates faster, it's going to be at the bottom first. So if I'm going to put this in words kind of thing, I'm going to say disc has a lower, I'm just going to put I, because we said what I was. Disc has a lower rotational inertia. It'll accelerate faster. and finish first. Certainly, if you're writing this on a test, you won't just put finish first, but reach the bottom first, have a lower time, however you want to do it. But I just want to at least spell it out in a way that you understand it here. By looking at this and drawing the picture may or may not help, but I've listed things out into like a little table. I wrote my formulas, and by looking at that, I can see what's going on as long as I understand the definition of rotational inertia. It's a pretty good question. I'm glad you brought it up because it's definitely one worth going over because it's completely conceptual, but it'd be a really good FRQ question, wouldn't it? To have someone compare and contrast why one would win over the other. Okay, so we've got that done. Let's go into new material. Where we are, we're in Canvas right now, and today's, I think, Thursday. Yeah, so we're on the bottom there. We've got a page that titled itself Notes about Torque and Equilibrium. So we're going to talk a bit about torque, kind of the easier parts of torque for a minute, and then we'll go into the rotational equilibrium with torque, and we're going to do some problem solving with that. And then there's a few problems with torques at angles. I think we might have enough time to get through all of it today in class where you don't have to worry about too much homework wise, especially if you've gotten a little bit behind over this last week. It's going to be an opportunity to get caught up. All right, so that's where we are. That's the direction we're going. And let's see if I can click on that. Yeah, look at that. Okay, so this is today's starting page. Here we've got torque is equal to RF sine theta. The R being the radius or the distance from center is going to be the radius. F is the force that's being applied because we know torque is a force that's causing rotation. So it's just force and how far away from center is that force being applied. And then we've got this sine of theta. We're going to look at this in more detail, but basically we're going to see where a line of action is and at what angle that force is being applied compared to the line of action. Okay, we get there's a good long paragraph sitting here that you can read through. It just says torque is rotational analog of force. We've said that before because force is for linear, torque is for angles. Like force, torque is a vector. For our purpose, we will treat directions as clockwise. Now, this is an important part. If the torque causes a clockwise rotation, we're going to call that negative. I think it even explains it in here. The way that you can think about it is, righty-tighty on a jar, like a top. As you screw it to the right, it goes down. And we generally say down is negative. So if the rotation is clockwise, we'll call that negative. If the direction is counterclockwise, we'll call that positive. And that way, that counterclockwise, if you're unscrewing a jar lid, and as you screw it to the left counterclockwise, it goes upwards, we'll call that positive. All right, so there's, I think that's what it's describing in there. And then we've got a couple of simple examples that we'll go through together real quick. A plumber applies a 20 Newton of perpendicular force. Okay, so the force equals 20 Newtons. The radius or the distance is going to be equal to 0.15 meters. It says it's perpendicular, so we know that the angle then would be 90 degrees. And what's the sine of 90? Anybody know?
It's 1.
Right, it's 1. And when we're doing sine here, we're doing it in degree mode. We're not in radians right now. We're back in degree mode. So when the angle is at 90 degrees, the sine of 90 is 1. So we don't have to really worry about it. I mean, you could write it into the equations, and we might sometimes, but it is just an extra step. It's multiplying by 1. Okay. It's asking us how much torque did he apply, and he said that it's in a counterclockwise, so we know it's going to be positive. So then torque, that Greek tau, is equal to force times distance, or distance times force. Sometimes I write it one way or the other. Order there doesn't matter. And then from the side, we've got 20 times 0.15. Put that into our calculator, and it's 3, right? Yeah, 3. And then the unit would be Newton meters because force and distance. Now you're asking yourself, wow, that's really easy. Can it really be that easy? And yes, it's going to totally start out that easy. start out that easy. Don't worry. I'll get to a point where you realize, okay, yes, now it feels like that AP class we're so fond of. Number 2, we have a water wheel radius of 3 meters. So the radius is 3 meters. Catches water on its rightmost edge. As the water falls, it applies a force of 100. All right, so force equals 100 newtons. How much torque is produced? Okay, well, the torque is equal to the force times the radius, which equals 100 times 3. So we should have 300 Newton meters. And if it's applying it to the rightmost edge, okay, so here's my water wheel. And then it catches water going this way, right? And that would be rotating, that's clockwise. So our torque should be negative 300 Newton meters. Now, that's right, correct? Yeah, that's right, because it's going to be going clockwise. So it's something to pay attention to. Drawing the picture helps. Let's see, did somebody try to come in? I thought it clicked, but maybe not. Let's see. Nope. Okay, awesome. Now this goes into just a little bit of notes, and it's just bringing back some reminders. I'll just kind of tell you, we're looking at this area real quick. If net force is 0, we know that net force 0 means that there is no acceleration and that the velocity is constant. It doesn't mean the velocity is 0, though it could be. It could be any value, but it's held constant when net force is 0. Well, looking at rotational motion, same thing when it comes to net torque. So we're looking on the right side now. When net torque is 0, the angular acceleration is 0, and the angular velocity is constant. It could be a constant 0. It could be a constant any number that you think of, whatever favorite number you want to have. If the velocity is constant, angular or otherwise linear, then the angular acceleration is 0 or the regular acceleration is 0. So these kind of go hand in hand. Now, I don't know why this page has this statement written again, so I'm just going to scratch it out. It's the same one that was written up above. Here it gives us some steps, how there's free body diagrams, identifying axis of rotation, writing net force equation, writing net torque equation, substituting and solving. Don't worry, we're going to do all of that by stepping through it. Then you're going to kind of understand the list. So I don't want to dwell on the list too much. What I want to do is put it into practice, and then we can see what's going on. Then you can go back and kind of appreciate the list. That brings us to sample problem number 3. Also, the sample problems they have here don't really apply to the list too much. When we go to the next page, it will. Okay. Everybody good so far? Everybody's awake?
For the one with the water wheel, why did we not include the sine theta?
Because that's a great question. I'm going to, let's go back to it. Remember when I said it's the angle that it hits according to the line of action? But I haven't really explained what line of action is at all. Let me draw the line of action into this. So let's just erase what we have. And then I'm going to draw the water wheel. Now the line of action is perpendicular to the pivot point. So if the pivot point is here, my line of action would be going along this direction. That's one line of action, okay? And then the water coming down is going this way. So it's perpendicular. So here, theta would equal 90 degrees. And then we said the sine of 90 is 1. And you're right. I could have definitely included times sine of theta. And then that would have been, oh, I hate that 3. Take that 3 off. Let's draw it again. 3 times 1. And we would have been at the same solution. It's a great question. And I'll try to make sure that I highlight the line of action as we're going along so that we can see. The tricky part is when we get to the last page of the day, we're doing 3 pages. This is the first of 3. When we get to the 3rd page, the way that they describe the angle, we've got to look at the line of action and actually determine, is that the angle value we should be using in our equation or not? When we get there, it'll make more sense. So did that help answer? Okay, perfect. I see that you nodded, so there we go. All right, sample 3. You observe that Alice and Bob are playing on a seesaw. When the two are balanced, okay, so let's draw a seesaw. There's my seesaw, and then I'm going to put a fulcrum right here. The fulcrum is just where it teeters back and forth. It's the pivot point. Two are balanced. Alice is sitting 1 meter to the left. Okay, so here's Alice right here, and her distance from here to here is 1 meter. From there to there, we've got 1 meter to the left of center, and Bob is sitting 0.75. All right, so from here to there, right from edge to edge, he's at 0.75 meters. Alice proudly proclaims, all right, let me put Bob in there, that her mass is 35. Okay, let's fit a 35 in there. What is Bob's mass? The two are, and it says they're balanced. Okay, it says balance means equilibrium. When we're looking at a seesaw, what we're really balancing is the torque, because when you're going up and down on a seesaw, you're creating an angular motion, right? In order to have an angular motion from balance, you've got to have a torque, because that's the force that causes that angular motion. So if they're balanced, that means the torque on the left is equal to the torque on the right. And another way of writing this would be the torque of Alice is equal to the torque of Bob. Okay. Now, the line of action for the teeter-totter or the seesaw would go right through the seesaw, and their forces are going straight down on either side. So their forces are at 90 degrees. The sine of 90 would be 1. So I'm not going to dwell on the sine of theta in this, because it'd be the sine of 90 on both sides. What we can then just focus on is say, well, the force times the radius is equal to the force times the radius for Alice and Bob. I'm not going to put the little A's and B's in there because my handwriting is just so messy. It would just get crowded, but we can understand that we're looking at that for each. So for Alice, the force for Alice is simply going to be her mass, 35, times gravity, which is 10. That gets us a force. And then her radius is 1. And then for Bob, we don't know his mass, so I'm going to put in m times 10 times his radius of 0.75. 35 times 10 is going to be 350, is equal to 10m times 0.75. I'm just going to use my calculator real quick. I have 350 divided by 10 and then divided by 0.75. I got 46.67 when I did the math. 46.67 kilograms would equal Bob's mass. Since Bob is heavier, he has a greater force. If the force went up, if it needs to stay balanced and force went up, we know the distance has to go down. And that keeps it balanced with Alice on the left. If it's going to stay balanced and the force went up, the distance has to go down. Okay. Seesaw problems are very common. And with seesaw problems, we're simply balancing the torques, knowing that the heavier person is going to be nearer the center because they've got more force, so they need to have less radius or less distance. Okay, it's a very straightforward problem. I want to make sure we're really comfortable with it. I'm about to scroll to the next one, which isn't terribly unusual, but it's going to have a couple of points along the way. So torques increase the further you are from the axis of rotation. Absolutely, that's really well stated. And it's in everybody's chat. So torques increase the further you are from the axis of rotation. Yes, because we know it's force times distance. If you increase that distance, the torque is going up.
Mr. Watley?
Yes.
Where did you get the 10 from again when you were finding force?
Because force is mass times acceleration. And I had the mass of Alice and I was looking for the mass of Bob. And in order to make their masses into a force, I used the acceleration of gravity and basically turned it into their weight, because your weight is your mass times gravity, right?
Mm-hmm. Yeah.
That's where the 10 came from. It came
Okay.
from little g. It's a good question. I'm glad we're engaged. I'm glad we're looking at this because we want to have a good firm foundation of this information because we're going to take it up a notch and apply it. Not quite yet, but we're going to get there. All right. If it's okay, I'm going to scroll up to the last one on the page, sample number 4. Here, they give us a bit of a picture and a description. We've got a gazelle noticing a particular tasty flower at the end of a log. So we've got that's kind of that weird picture sitting with the gazelle. However, the flower of negligible mass, so that means we don't care about its mass, and log overhang a high cliff. So that's what we're seeing in this picture. So that rectangle he's standing on is a log overhang a cliff. The log is 5 meters long. Okay, so I'm going to just say from here to here, this is 5 meters, going all the way to there to all the way to there, with a uniformly distributed mass of 150 kilograms. So I'm going to write on the log 150 kilograms. The flower is 1.8 meters away from the edge of the cliff. Okay, so from here to here, this is 1.8 meters from there to there. Okay, 1.8 meters. All right, I'm good with that. If the gazelle is 40 kilograms, okay, so let me write on him 40 kilograms, and walks the full 1.8 meters away. So he's standing on the edge. The picture doesn't look like it, but he's standing on the edge. Can it reach the flower without tumbling to, all right, what the question is saying is, when the gazelle walks 1.8 meters off further than the ledge to the end of the log, will this cause the log to rotate and flip over and be a really bad day for the gazelle? Okay, that's what the first question is asking. Let's stop there and try to answer that question. Okay, now when we're looking at the log, I'm going to draw the log over here. Normally with a teeter-totter, we're going to put the pivot in the center. That's normal, but in this case, the pivot is going to happen at the edge of where it's connected to the cliff. So I'm going to circle that in black. You can kind of see that. That's where if it were to start to rock, it would rock right on the corner of that ledge. So we know the pivot point really happens like right here. Okay, it's to the left side. That's where it would rock as it rotated over if it were to fall over. Okay. Now, the log itself has the mass of 150, and that mass, the force of gravity occurs at the center. Okay, so if this log is 5 meters long, at 2.5 meters, which would be about right here, this is from here to here is 2.5 meters. This is the place that the force of gravity for the log occurs. All right, this takes a minute to process. The force of gravity for an object occurs at its midpoint, where the center of mass is located. Okay, the center of mass for this log is at 2.5 meters from either end. It's at the middle of the 5 meters. That's the force of gravity for the log. Now the gazelle is out here on the edge, and his force of gravity is happening 1.8 meters from the pivot. I want to compare the two torques, the left side and the right side. If the left side torque is bigger, the left side is going to go down and it's a bad day for the gazelle. If the right side torque is bigger, the right side is going to stay in place because the ground is keeping it from rotating, and the gazelle gets to live another day. Okay, so let's compare the torques. I want to compare the torque of the gazelle compared to, I'm going to put a box. I don't know if it's equal, greater than, or less than the torque of the log. Okay. The torque of the gazelle is calculated by its mass, 40, times gravity, so that I have a force, and I multiply by the distance from the pivot point, 1.8. That is the torque of the Gazelle. Let's go ahead and calculate that value, which would be what? 400 times 1.8. 400 times 1.8 on my calculator gave me 720 Newton meters. Okay, I'm just looking at magnitude right now. I don't care if it's positive or negative. Let's just look at magnitude. Let's do it for the log now. The torque of the log. Well, the mass is 150. The acceleration of gravity is 10. So that's the force. Now we need to know the distance that force of gravity is from the pivot point. Okay, well, if from here to here, I'm on the top of my picture right now. If this is 2.5 meters, and we know that the ledge is 1.8 from the pivot point to the Gazelle. Pivot point to the Gazelle is 1.8. So how far is pivot from force of gravity? Wouldn't that be 0.7? Wouldn't this section right here have to be 0.7? Because that 0.7 plus the 1.8 gives us the 2.5 for that whole side. So the distance of the force of gravity from the pivot point for the log is 0.7. Take that for just a second and look at it, make sure we understand. The pivot point is where the log starts to overhang. And from that pivot point to the edge of the log is 1.8 meters. The force of gravity is at the midpoint, 2.5. So from pivot to midpoint is 0.7. Okay. If we've got that, we've got 150 times 10 gets us 1,500, right? That's pretty obvious. Times 0.7. My calculator says that's 1,050 Newton meters. That means the torque of the log is larger. Gazelle's having a good day. The Gazelle has not created enough torque in order to rotate that log and tumble down the cliff. All right, so we've answered the first question. All right, hope we feel good about that. Let's take a breath. The next question says, how big is the normal force acting on the log? Okay, let's go back to the log. Draw us a new log. Good morning. Good morning. We said the center part of the force of the log has our force of gravity for the log. And then we've got the Gazelle sitting on top of it over here. It has its own force of gravity. This has a mass of 40. This has a mass of 150. So we know our force down. If we add these up, we've got what? 40 times 10 plus 150 times 10. That would be what? 400 plus 1,500, which would be 1,900 newtons of force going down, right? I have a total of 1,900 newtons of force going down. Is this log moving? Correct, it's not. I'm responding to the movement of heads saying, no, it's not moving. That's right, it's not moving. So the force down has to be balanced with the force up, right? The answer is yes. Balanced forces means no acceleration. In this case, a constant velocity of 0. So if the total downward force is 1,900, the total upward force must be 1,900. And there's only one upward force present here, and that is the force normal. So the force normal of this system is equal to 1,900 newtons.
Question. Since it's like rotating off the edge, wouldn't it be that like it like rotates a little bit and therefore decreases the force normal?
It's
Or
not
no?
rotating at all.
Okay.
The torque on the right side, this would be like if you sit on a teeter-totter and a 1-year-old sits on the other side, and you know how you don't move? It's like that. It's like when you were little and you got on a teeter-totter and there was like a really big kid sitting on the other side and you couldn't get that thing to move because the kid, the big boy on the other side was straight off the football field and wouldn't, you know, it was way heavier than you, right? So I get the idea. It's like, well, hold on, it should be doing something, but the torque on the right is bigger than the torque on the left. So the torque on the right is winning and it wants to rotate to the right, but the ground is there, so it's not doing anything. It's sitting perfectly still. It's going to take a lot more force on the left side it's going to take a bigger mass on the left side in order to overcome the torque on the right to then get a positive torque, spinning it in the counterclockwise direction. Here, this is when we go back to the bottom of the last page when it said draw a free body diagram. I sort of drew a free body diagram and said, okay, what I have is, if I made this a little bit nicer, let's take that off. Let's take this off. All right. And then we would have this downward force of gravity from the gazelle. So I'm going to do FG with a capital G for gazelle, and this is FG for the log. That's my free body diagram. And then it's sitting on the ground, so I know I have a force normal up. And since it's not moving, it's balanced forces. It's okay. This takes a little bit to process. Don't worry. We're going to get a little bit more practice, which will make it a little bit easier. Now, the last question on this says, where does the force normal act? Here I drew it in the middle, and that's not where it occurs. So I'm going to erase it. Let's talk about where does the force normal act. The force normal acts at the pivot point. So if the pivot point was over here, like here are my pivot points, so my force normal actually acts right here. And if we think about it, what if that log starts to pivot and wavers back and forth? That pivot point is the only point of contact, and that would be where it's in contact with a surface. So that's where the force normal is going to act. So your force normal acts at the pivot point, and the force of gravity acts at the center of mass. Isn't that awesomely confusing? But force of gravity acts at center of mass. Force normal acts at the pivot point. Good news is we finished that page. Let's take a look at the next one and see how far we get. We're pacing a little bit slower than I was anticipating, but that's okay. I think taking the time and getting the understanding is going to be most important. All right, I'm going to advance to that next page. This is what this one looks like. We've got a tabletop with a stack of books. Looks like the tabletop has a 100 kilogram mass. The stack of books has a mass of 25 kilograms. It says determine the forces that each leg exert on the table in the table for the picture below. The tabletop has a mass of 100 kilograms and the books have a mass of 25 kilograms. They've done a really nice job for us in at least drawing us some of the forces. The legs are pushing up on the tabletop. That's why the tabletop's not falling to the ground. So the legs give us an upward force of F1 and F2. We know that the tabletop itself is going to have FG going down from its center. And we also know that the stack of books would also give us a force of gravity going down from their center. Okay. I'm going to scroll this up just a little bit because we've got the picture. We've got the idea what's going on. Let's scroll up just a little bit. See, we have what? Draw a free body diagram, draw a free body diagram for the books and for the tabletop. Okay, great. There's a couple of things that I want to do real quick, and I just want to label. So I've got, what did they say this was, 25 kilograms. Okay, and then they gave me all these dimensions and lengths. Let's add these up real quick. So the total length from here to here, let's see, we have 1.2 plus 2.4 plus 0.8. Let's see, that's 4.4? Yeah, 4.4 meters from there to there. So that means that right here, where my force of gravity is going to happen, this is the 2.2 meter mark, because that's the middle. If the whole span is 4.4, then I know where force of gravity is at the center of the mass. That's going to happen at the 2.2 meter mark. And then the force of the books will be right here at the 1.2 meter mark. Okay. I'm doing this for myself kind of, but it helps me see things when I'm going back to answer questions. That's all. All right. So let's take a look at this. Draw a free body diagram for the tabletop. Okay. Well, we know we've got the legs pushing up. So I have force 1. They labeled it force 1 and force 2 for me. So I'm going to use the same labels. Force 2. The force of gravity going down is at the center. So this is force of gravity. If it helps, what you could say is this is mg, but we can say like mass of the table times g, if you like. Whichever works. I don't really care. And then we have the force of the books. So we have Fg, which here is the mass of the books times gravity. Okay. However you want to look at it. I didn't want to confuse you with Fg, because it's the force of gravity of the books, force of gravity of the table. And I'm just trying to align it to the picture. Okay. That's what's going on with the tabletop. Draw a free body diagram just for the books. Okay, well, that's easy. The books, they're not accelerating, so we know we have balanced forces. We have force of gravity down, force of normal up. It's on a tabletop. Let's scroll that just a little bit so I can draw. I have force normal, and I have force of gravity. Okay, so far so good. We're kind of walking through the steps that were on the front of the first page there at the bottom where it said, hey, first draw a free body diagram. Next, do this, do this. Okay, looks like this page is going to walk us right through it. All right, review. What type of forces does the stack of books exert on the table? What type of force does what's the answer to this question? What type of force is that?
Gravity.
Gravity, yeah. Now it says, what law is this? In my answer, I put the books exert mg on the table or force of gravity. It is equal in magnitude and opposite in direction, Newton's third law of the force the table exerts on the books. So there is a Newton's third, the books are pushing down, and so the tabletop pushes up. And that's what we see in the second free body diagram. When it says, what law is this? It's just asking us to recall Newton's third law. What is true of the tabletop's velocity? What's true of the tabletop's velocity?
It's not moving.
Yeah. Well, you said it like you were scared too. Yeah, it's not moving. The velocity is 0. All right, so let's see. We can say this is the force of gravity. What's true? The velocity equals 0 meters per second. And let me also put it's constant. Right? That's true of the tabletop or the table's velocity. We know it's 0 and we know it's not changing. And so the next question says, what does that mean?
Forces are balanced.
Yeah, the forces are balanced. So let's say the net force equals 0. And we can say that that means acceleration equals 0. Okay. And just to keep things easy for me when I'm writing this out, when I refer to Fg for this problem, I'm going to go ahead and just call Fg, I'm going to call this one Fg, and then I'm going to call this one force of the books. All right, FB. Because when I'm looking at it, when I see books, or when I see B, I'm going to know that means books. It's just going to be a shorthand for writing these out. And also, when you look back at it, you're like, well, which one's the books? And I don't want too many subscripts as I'm showing it to you, because when you look back at it, I don't want it to be confusing. So let's call the force of the books down FB, and then FG can be the tabletop's force of gravity. So here we need to write the net force equations for the tabletop. Okay, well, there's nothing in the X direction. So I'm just going to write the net force. So the net force in the Y direction. And here, we had going upwards, our positive direction, which would have been F1 plus F2. And then in the negative direction, we had FB, the force of the books, and we had FG, the force of gravity from the tabletop. So that's my net force equation. If I wanted to put numbers to that as much as I can say, well, F1 plus F2 minus the force of the books, which would have been what, 25 times 10, minus the force of the tabletop, which is, what was the mass of the tabletop? 100, okay, sorry. 100 times 10. And we know that this is going to be equal to 0 because we said the net force is equal to 0. So F1 plus F2 minus 25 times 10 minus 100 times 10 is it going to be equal to 0? And that's coming straight from our free body diagram. We have F1, F2 going up. We have FB going down, FG going down. Fair so far? What's really cool is now we finish a whole half of the sheet, right? It's got to be easier from here. The second half can't be as bad as the first half. Take a breath and we hope. Okay. Why can you not solve the equation for the forces the legs exert on the tabletop? All right, so let's scroll back up. It's saying, why can't we solve for F1 and F2? What do you think?
Because they're two unknowns in one equation.
Got that right. Somebody paid attention to math class. Absolutely right. If you have two unknowns, two variables, you need two equations. Right now, we have one equation and two unknowns. You really can't solve for them with confidence. I mean, you could make stuff up, but when is that going to be right? All right, so the next statement says, so if we can't solve it, now what? You currently have two unknowns, but only one equation. You need a second equation. So that's not really a question. It told us we need a second equation. So let's go to what it says next. What is true of the tabletop's angular velocity?
0.
It's 0, right? So the angular velocity, this guy is equal to 0. And we could also say that it's constantly 0. So I'm going to say it's constant, just like before. And what does that mean? If angular velocity is 0, what does that mean?
Sum of torque is 0 and alpha is 0.
Exactly right. Alpha is our angular acceleration, and it is 0. And then our torque, or at least our net torque, otherwise written as the little summation sign, net torque, is equal to 0. The net torque, or the summation of the torque, is 0. If we go back to the gazelle on the log, it didn't rotate, so the net torque was 0. But we understand there was a torque from the gazelle, and there is a balancing torque, right? It wasn't moving, but there was a force at an angle being applied. It was there, just wasn't enough to make it rotate. All right. So write a net torque equation for the tabletop. Now, all of a sudden, we're like, wait, what? That's okay. This is where we need to take notes and make sure we're paying attention. So let's wake up real quick. Let's shake off the cobwebs of the morning, and let's draw that tabletop one more time, because I need to bring it somewhere where I can see it. So there is my little fancy dancy tabletop. Okay. I had, I think it was F1 on the left, F2 on the right. We had MG here at the midpoint, that FG, and then we had the force of the books. We call that FB, like right there, ish. Okay, ish, sort of. Now, for a table to rotate, could this tabletop rotate from the center? All right, I'm so glad I can at least see one head shaking her head no. She's like, no, it can't, because it's got legs. I mean, it would be really weird for me to see a table all of a sudden spinning from the center. But if that table were to flip over, where would the point of rotation be? If you're home and you're really mad at your mom and you're like, you know what, I'm going to show you, and you flip a table over, where would the point of rotation be?
legs.
Did you say, what'd you say?
Sorry, the legs.
At the legs, at the side, right? So what we're going to do is we're going to make the point of rotation. We're going to select the left end as the fulcrum or the pivot point right here. Okay, that is our pivot point. And we're going to, that means our line of action is going to go straight. I need to change colors just so it doesn't get confusing. I'm in black. I'm going to put our line of action is going to go right through here. That's our line of action. And let's pick another color again. So if our line of action goes through the middle like that, and it's going to rotate based on that left end, okay, that means all of our forces are perpendicular in this case, aren't they? Perfect, because we know that the angle is the sine of theta, and theta is 90 degrees here. If theta is 90 degrees, sine of 90 is 1, we don't have to worry about the angles. If it makes you feel good, we can write it in. For the first sentence, I'll even write them in, but let's just know that this here is 90 degrees, okay? Now, torque is force times distance, right? And if the torque, no matter what it is, if the distance is 0, if the force is anything, if the distance is 0, what does the torque have to be?
0.
0. Absolutely right. So that means this one right here, that's going to have a torque of 0 because its distance is right on the pivot point. So this one won't be included. That one's not going to be included because the force is acting on the pivot and therefore does not apply any torque. I mean, we can say, okay, but what if it's 100 newtons? Great. 100 newtons times the distance. What's the distance? 0. 100 times 0 is 0. Okay. Now that we know that that one's gone because the distance is 0, we understand the pivot point is on the left side. If the pivot point there is on the left side, the force of the books really wants to try to get the table to rotate this way. The mg also really wants the table to go this way, doesn't it? If I were to take the legs off the table, make that a pivot point, doesn't gravity make it want to tip downwards, making it go into a clockwise direction? On the right side, this upwards force wants it to go that way, which would be a counterclockwise direction. So now we've got 3 forces, 2 that are clockwise, 1 counterclockwise when we're considering calculating our torque. So now what I want to do is actually write the net torque equation for the tabletop, okay? Anything that is counterclockwise is positive. Anything that is clockwise is going to be negative. And when we sum them up, they equal 0. So my net torque equation, I'm going to do the summation. The summation of the torque is equal to, let's see, let me write these real quick. This was the force of the books. This is the force of gravity. And then this was F2 over here, okay? So then if I'm going to just go from left to right, I would say negative FB times the distance of B times the sine of the theta minus FG. Or if I put that in parentheses, it would help, wouldn't it? But I'm not. Times the radius or the distance that that's coming from, times the sine of its theta, plus F2, the force of 2, times the radius coming from 2, times the sine of its theta, all has to equal 0. That's a mouthful. But we're looking at, let's see, let me change color. Let's do red. this, well, that didn't change my color at all, did it? This is my torque from the force of the books. This is my torque from the this is the, come on. Oh, Wally, draw. That's the torque from the gravity, from the force of gravity. And then this is the torque from, what they call it, F2. And I'm summing those torques together. Clockwise are negative, counterclockwise is positive. Just remember the jar rule. You know, righty tighty goes, screws it down, down is negative. Okay. I'm monitoring the chat too. So if you need to put something in there, even if it's just in frustration, totally go for it, because that's the last question of the page. Solve your system of equations to determine the force that each leg exerts on the tabletop. Okay, what I'm going to do is I'm going to take my net torque equation. I'm going to plug in numbers and see what we have. Let's see. What do we have? Let me scroll this up. So we take our net force is equal to, okay, we said it was negative. The force of the books was, the mass was 25. So what would the force be?
250.
Yeah, 250. It's just mass times gravity, right? So that's going to be 250 times, what was the distance from the left edge that the books were?
I think 1.2.
Yeah, I think you're right. 1 point, that sounds about right. 1.2. And then the sine of 90 is 1, right? So I'm done with that one. And then I'm going to say minus the force of gravity from the tabletop. The tabletop, it was 100. I think that was a good clean number. So if the mass was 100, the force of gravity would be 1,000, right? So minus 1,000 times, what was the center of the tabletop? I know I did this one. What did we say the center of the tabletop? 2.2?
Yeah.
Okay, perfect. All right, so 2.2. And then the sine of theta, sine of 90 is still 1, so we don't have to worry about that. Now we're going to add in F2. Okay, F2 we don't know, right? That's something we're still trying to figure out. So then we have F2 times its distance. And the whole tabletop was 4.4. So from the far left side where the pivot is to the far right side, that's 4.4. And when we, and then it also had the 90 degrees. So the sine of 90 is 1. So we don't have to worry about that. That is equal to 0. Well, that's a single equation with one variable. So we can totally solve this. All right, let me break out my calculator. I've got 250 times 1.2. So 250 times 1.2. That's right? Yeah, so that's negative 300 minus 1,000 times 2.2. I'm terrible at doing math when people are watching me, so I'm going to do it in my calculator. 2,200 plus 4.4 times F2 equals 0, right? So negative 300 minus 2,200 would be negative 2,500 plus 4.4 times F2 equals 0. If I add 2,500 to the other side, I get 4.4 times F2 equals 2,500. So now I've got my 2,500 divided by 4.4, and I get not a very clean number, but it's a number, 568 newtons equals force of 2. It's not terrible. All right, solve your system equations to determine the net force. Okay, perfect. All right, we have 568.18 newtons equals force of 2. And this is assuming I didn't make any silly math errors along the way.
Mr. Watley,
Yes, what's up?
is it like always going to be 90 degrees, or is there an instance? Okay.
Yeah, and in our practice work, after we get done with this page, go into our practice work, I think what I'm going to do is skip around and work with a couple of them that aren't 90 degrees and show that to you. The good thing is we're starting with the easy 90 degrees, but we're going to see here in a couple minutes some that aren't. I mean, the good thing is like a tabletop, those are 90 degrees with the legs and we put something on it, that works. But what happens if, you hit something at an angle, or what if you have something like before it was like a water wheel. What if you took a rock and you threw it at an angle and it hit it and caused it to spin? That rock's not going to come at a perfect 90-degree angle. So we'll see it there. Let's finish this up real quick. If we go back to the first page of this, we had that other equation right here, correct? So that was F1 plus F2. All right, so let's write that down. We said that the summation of forces in the y direction equaled F1 plus F2. Then we subtracted, oh gosh, what did we subtract? 25 times 10. So I'm just going to put 250 minus 250 minus, what was the other one? 100 times 10. So that's 1,000 equals 0. Minus 1,000 equals 0. All right, that's the net force. This is from page 1. I'm just going to put page 1 here. So no one gets confused like, well, where did that come from? Totally cool. All right, so we have F1 plus, we said F2 is 568.18, and then minus 250 minus 1,000, that'd be 1,250, right? Yeah, equals 0. So 568.18 minus 1,250 gives us F1 minus 681.82 equals 0. So that means F1 equals 681.82 newtons. So here's my F2 and here's my F1. And it makes sense that F1 is bigger than F2 because the stack of books is closer to it. So it is supporting the books more so than on the left than it is on the right. So our answer at least makes sense. And that's something to always consider when you're doing the work is the solutions you're coming up with, does it pass the sniff test? Does it make sense what we're doing? And here it does. It absolutely does. This finishes this sheet. This was kind of the introduction, continuation of torque with some explanation in how we're going to use it in order to solve for multiple variables. Okay. This that we just did is going to completely be continued in the next class. We're going to do notes and then practice problems, but let's go into the practice for today. That is this sheet. Okay, we don't have a lot of time and I don't want to talk the entire class. So let me hit some highlights. I'll tell you what, I'm going to do number 4 with you and that's it. I'm going to do number 4 and then I'll let you do the rest of the page. There's only 8 total. It's not terrible. All right, so let's do this. All right, I picked number 4 intentionally. So you asked me, is it always going to be 90 degrees? And here we've got a photo that shows us that ain't 90. So let's take a look at things. A torque of, all right, so I'm going to put my margins. The torque equals 857 Newton meters. Is caused by an unknown force applied to a gear that has a radius of, okay, so radius equals 0.05 meters. Make sure if you see something in centimeters, you're converting it to meters. We know that. The unknown applied force was applied at an angle of 30 degrees to the rotation's tangent. So they've given us a picture. How much force had been applied to cause the, all right, so we're looking for force. Force equals question mark. We know that the formula, don't go too fast on this because there's a catch me on this, all right? The formula is equal to force times radius times the sine of theta, okay? Now, let's go to the picture real quick and talk about it. Here's the point of rotation right there. I just put a big dot in the center of the picture, and I want to draw the line of action. Here, the line of action comes through right here. That's my line of action. You can also draw lines of action straight up, depending on where the force is coming from. But here it makes most sense to draw it horizontally. Okay. Now, if I was to choose the angle to put into my formula, what angle am I going to put into my formula?
60 degrees?
60 degrees, absolutely right. See how tempting it was to be like, oh, dang, that's 30 degrees. No, this theta is equal to 60 degrees. So here we would come in we would say what, well, we need to rearrange this formula, don't we? Let's do a little bit of rearranging to make sure we do this the right way. We're solving for force, so that means torque divided by R times the sine of theta is equal to force. So then we would say, okay, the torque is 857 divided by 0.05 times the sine of 60 degrees. Make sure you put this in parentheses if you put it all one sentence into your calculator. And that is going to equal your force. All right, so that's something we've talked a little bit about, that line of action. You don't have a lot of experience with it, but we've talked about it today. And we want to make sure that we understand that in our calculation, if we're looking for or identifying that theta, it's based on the line of action, not based on how they drew the picture or anything else. We need to make sure we understand that the formula works for the theta that is line of action to where the force is being applied or how the force is being applied. All right, that brings us into being in class for, I've been talking for just over an hour.